these are the three start equations from last time, and for this morning. And I'm sure you all used the lunch break to perform the Legendre transform check. Indeed, they can easily go from one to the other. And all of them were derived in the limit of large little m, including the coefficient, where I remind you that what you really mean by lambda, big lambda, depends on the regularization scheme. And this was true, these formulas are true in a particular regularization scheme known as dimensional regularization bar. Whatever it is, doesn't matter. And the only place this entered was in the one-loop computation of how the scale change is we integrate out a quark. And the only other number that we needed was an order 1 number in front of the gaugino condensate of the Q gauge theory. And I said it's 1 in this normalization, and I promised you that I will present a computation justifying this. So the assumptions I still owe you is that in the Q gauge theory, there is a gap, NC ground states, and there is a gap. And number 2, that the coefficient of the gaugino condensate is 1 in this particular regularization scheme. And that's it. Everything else so far follows from it. And then we said that these formulas are kind of interesting because we can derive from them various expectation values. Let me just write one of them. I don't want to get any factor wrong. So in particular, we found this expectation value for the meson M, which is extremely surprising. It's surprising for two reasons. First of all, the quarks are massive. They weigh a ton. We integrated them out. And yet, this quark bilinear has an expectation value. That's surprise number 1. Surprise number 2, if the number of flavors is larger than the number of colors, then the rank of this matrix M is constrained to be at most NC, whereas the right-hand side has an arbitrary rank. So this by itself should be surprising. We take a classical object, this quark bilinear, and classically, and therefore also for every single configuration in the functional integral, the rank of this matrix M is constrained. So this formula for the rank is true order by order in perturbation theory. It's true non-perturbatively. It's a property of every single configuration in the functional integral. And yet I claim that the expectation value does not satisfy this equation. I'll have more to say about that. So all this was derived when the mass little m is very large. But then I argued that these formulas have to be exact. They have to be exact because the effective superpotential has to be holomorphic in the mass here, or conversely, it should be holomorphic in big M and big S, if we work in this one. And as holomorphic functions with big M, the mass, and lambda, and little m, this is all you can write down. So all these formulas are uniquely determined by the symmetries in holomorphy up to the overall normalization here, which we tied to one coefficient we did not compute, which was the gaugino condensate in the Q gauge theory. So now what we want to do is crank the mass down and see how we can interpret these formulas when the mass is very small, and see what this thing tells us about the theory with infinitesimal mass or maybe with zero mass. So these formulas should have an interpretation then. Now this is very common in duality and very common in all the dualities, ranging from the simplest dualities in field theory all the way to ADS-CFT. You compute some formula which turns out to be exact for one reason or another. And the physics words which go with it, the physical interpretation, is different at different corners of the parameter space. So for example, in n equals 4 Young Mills, you do a certain perturbative computation and you find some dimensions of operators or something is protected at weak coupling. And at strong coupling, it derived the same answer using some supergravity computation. We'll do the same thing here, where we derived all these formulas when the mass is large. And now we ask ourselves, what do these formulas mean when the mass is small? And also, what does this have to do with the Wilsonian action describing the light particles? Because all that describes the theory with a gap, no massless particles, only as a function of the parameters. So this is a summary of what I said this morning. Are there any questions before I proceed?
Well, NF is bigger than C, then the effective potential of M is 0.
I'm sorry?
In the third formula, when
Yes.
NF is bigger than NC, then the matrix M is degenerate, then delta M will be...
Well, that's surprising. On one hand, this is an excellent point that you're making, that if we take the view that the determinant of M is 0, here it appears in the denominator for NF bigger than NC, then how can that be true? Yet, the expectation value seems like it makes perfect sense. So, since we derived this formula starting from here, the way we proceeded, we actually started here. And then we differentiate with respect to M, we find the expectation value. This is how we do a Legendre transform. You differentiate, you find the magnetic. So H is the magnetic field, M is the magnetization. That's why the letter M. So this is the magnetization, this is the derivative with respect to the magnetic field. You find what you find, you perform the Legendre transform when you find this. Already here you could ask this question. But here it was a result of a computation. The determinant is not 0. Okay, so we conclude that even here the determinant cannot be 0. So for NF less than NC, there is no puzzle, but for NF bigger than NC, this formula is very confusing. This formula is actually very confusing for another reason. Let's NF be bigger than NC. Then the exponent here is negative, which means that this scales like 1 over lambda. What happens at the weak coupling limit? For weak coupling, lambda is very small. We take lambda to be the scale is very low. And this formula diverges. So for NF bigger than NC, the denominator has to be 0 for the reasons you said, and it's obviously not. And second, if I take the semi-classical limit of this formula, big lambda going to 0, this thing diverges. This also sounds crazy. Even more so when NF equals NC. When NF equals NC, this exponent here diverges, and also the coefficient here vanishes. So all this is just to say that there's clearly something to understand. So all these formulas make perfect sense when the masses are big. And our intuition about the rank and the determinant makes perfect sense. And then we say that using holomorphy, this must be the answer when the masses are small, but non-zero. But on the other hand, as you said, it doesn't make any sense. So something will have to give. So that was the question. I'm going to answer this question in this talk. Any more questions about lunch now that everybody is sleeping? Does the wireless work now? Can you watch this? Yeah? How's Brazil doing? Fortunately, the NBA is not at this time of the day. So we would like to understand all this story. So these are the answers, and the question is, what's the interpretation of that? So we would like to understand all that in the limit when the mass is small. So now we kind of put the answer aside, and we start, what do we know when the mass is small? Well, first thing we do is set the mass to 0. And we discuss the moduli space of vacua. And already classically, we saw that the story of what's the modular space of vacua is completely different depending on whether the number of flavors is less than the number of colors or larger or equal than the number of colors. So let's start with the number of flavors is less than the number of colors. So recall that classically, we had a modular space of vacua, which was very easy. It was the space of the matrices M. And for expectation value of M, the gauge group, which was SU-NC, is now spontaneously broken to SU-NC minus NF. So as we go to low energies,
we have these moduli, and f square of them, and some gauge theory, SU and F, NC minus NF gauge theory.
And then we ask ourselves, what happens next?
Well, this gauge theory will confine, and we'll have a gap, and everything would be as before. And the question we ask ourselves, is there or isn't there any superpotential which is dynamically generated along the modular space of vacua? Well, we have a candidate one up there. M is not quite the same thing, but they're not that different. Semi-classically, they are the same. So can we use the formula above to be a superpotential on this modular space of vacua? The first condition we have to check is there anything which is invariant under the symmetries, holomorphic, and has the right limits? It turns out that there's a unique formula that can be written down, which is the formula up there. So we attempt to write a Wilsonian action so this is some number which we still need to determine. And based on symmetries, it should be this lambda to the 3nc minus nf over the determinant of m. All this raised to the 1 over nc minus nf. And there should be some coefficient here. This is based on symmetries alone. So all we need to do is check whether the coefficient is 0 or not. If the coefficient is non-zero, then the term is there. And we can do it in various special cases. One case we can do it is nf equals nc minus 1. This is particularly interesting because for this value of the number of flavors, the gauge group is completely broken. So the cast of characters at low energy is just these mesons m. There is no strong dynamics at low energies, nothing fancy we need to understand. Everything is weakly coupled. And then we can ask, do we generate such a term? The leading non-perturbative effect in this case comes from instantons in the group. I'm sure you've heard about instantons, either in graduate school or by other speakers. I will not explain it here. And it will really be outside the scope of these lectures to present the instanton computation. If you're really interested, you can read about it in the literature. If you do an explicit instanton computation, you find this answer with a non-zero answer. In fact, you can even nail down the coefficient in the same celebrated regularization scheme. And the coefficient turns out to be 1. And the coefficient turns out to be 1, which sure enough is precisely the coefficient that we see up there for a totally different interpretation. So in this case, instantons lead to this answer. This result is significant. As a check, notice that in this case there is no fractional power. And since there is no fractional power, that's good, because fractional powers are associated with some strong dynamics in the infrared that gives us different vacua. But in this case, there is no strong dynamics in the infrared. So this computation is a completely well-defined, weak coupling calculation in field theory. And it was done a quarter of a century ago with this answer. It's actually embarrassing because it's more than a quarter of a century ago. Once we have this answer here, now this is a Wilsonian effective action, we can ask, what happens when we turn on masses? So we can turn on the mass. The mass is infinitesimal, we turn it on. And now we can integrate out the massive quarks and correspondingly the massive components of the matrix M and derive from here all the answers for fewer flavors. This is just algebra, nothing more than algebra. Let the matrix M, little m, the mass M, be M1,
M2, and then 0. And derive the formula for fewer number of flavors. So integrate out some quarks and leave the rest. And sure enough, it gives us the same coefficient as there. In fact, all the coefficients are tied together. So we derive the answer for NF less than NC minus 1. You could also ask, can we derive this formula directly in the low energy theory without integrating out anything? Answer yes. We said that in this case, there is a remaining gauge group. The scale of that gauge group depends on big M. That same story with gaugino condensation gives us this formula. And again, the coefficient works. So all this gives us a number of consequences. So now let me enumerate consequences. First of all, for NF less than NC, the formula above, which was derived for large M, large masses, can be equally well derived for small masses, with a slightly different interpretation. The interpretation here is that this is a Wilsonian action along the modular spatial vacuum. Lesson number 2. We proved in the first lecture a non-renormalization theorem. And I briefly said it here, and I was asked in more detail later outside of coffee, whether it's true non-perturbatively. And in the case of the West-Domino model, the non-renormalization theorem is true non-perturbatively. Now we see that in the case of gauge theories, the non-renormalization theorem is not true non-perturbatively. It's true to all orders in perturbation theory, but not true non-perturbatively. In other words, the non-renormalization theorem, which it has a perturbative proof, and it also has the holomorphic proof, the one that I presented here. The holomorphic proof allows us to have such terms. Let me write the coefficient here, now that we know what it is. NC minus NF. So holomorphy alone determines everything except the normalization, except the overall normalization. But we see the general rule. Once my 3 rules, symmetries, holomorphy, and various limiting cases, these 3 rules allow a certain superpotential. That superpotential is generated. And this doesn't violate existing facts. So the non-renormalization theorem, which is true perturbatively, is not true non-perturbatively. This is extremely significant because it tells us that dynamical supersymmetry breaking is possible. If the non-renormalization theorem were exact non-perturbatively, then we could not have broken supersymmetry dynamically. And I'm sure this is something that Michael will explain in more detail tomorrow. Next consequence of this computation. We did the computation in one case, with instantons, and we found the coefficient here 1. This number is non-zero, was shown to be non-zero, and we found the coefficient. And once we have one coefficient, the whole story ties together, all the coefficients. But now we can go back and prove all our assumptions from yesterday, from this morning. This morning I made a number of assumptions. That the pure gauge theory confines, has a gap, has a superpotential, the lambda-lambda condenses, and the condensation of lambda-lambda is big lambda cube with a coefficient 1. Here is a derivation of this computation. We do a computation in a different theory. We do a weak coupling computation. This is an instanton computation. Everything is completely well-defined. We don't need a lattice or anything. Just sit down and we compute the coefficient. We prove that it's non-zero and we find what it is. And through this long chain of reasoning, it's actually not that long, we derive an answer about correlation functions or expectation values of different observables in many, many different theories in a regime which is extremely strongly coupled. I don't recall another example of that in physics. We do a weak coupling calculation here, and the whole non-perturbative answer of structure of the theory is derived. So this is again kind of a duality. Do something with weak coupling and we find answers at strong coupling. So I promised you I had this debt that I said I still need to prove this gap that we had. That proves the gap, yes.
Yeah, so where the instanton numbers goes into your effect?
This is a single instanton. And the way to see that is that if you recall this formula, this thing, e to the lambda to the 3nc minus nf is e to the minus a pi squared over g squared.
with precisely this normalization. So that was always true. In the case of 3n's with NF, when the exponent here is 1, then we see that this thing is proportional to e to the minus 8 pi squared over g squared. That's why this is a single instanton effect. You can also check it differently. The system has various anomalous symmetries that the instanton, a single instanton violates, and you can check that this term violates the anomalous symmetries by precisely the right amount. So I did it briefly here, but the important lesson I would like to extract from all this is that for NF less than NC, we can actually nail down all the coefficients, prove that this superpotential that we derived there is actually correct also at small masses, and by doing that, closing all the gaps that are left before. However, there's one kind of disturbing fact about it, which I'll write here. That if we look at the potential for the theory without the mass, the potential along this direction M for the Q's looks like that. The Kähler potential at very large field strength can be easily derived, so that the theory here at very large M is just a theory of the free quarks. Everything is weakly coupled. We can derive it from the classical Lagrangian. So from the classical Lagrangian, we get the effective Kähler potential, which with the correct normalization is twice trace M dagger to the 1/2. You see M's is like a quark bilinear. So the M dagger has 4 quarks. We take the square root of that, so it's like a canonical Kähler potential. So we know the Kähler potential, and we know W effective. It's what appears up there. So we know W, we know K, we can compute the potential, and the potential slopes to 0 at infinity. This is also a bit surprising. We started with a theory that classically had an infinite number of vacua, a continuum of vacua, inequivalent vacua. Quantum mechanically, the system runs away to infinity. So quantum mechanically, this system doesn't have any ground state, which is somewhat unusual in field theory. If we turn on the mass, so we take this formula that we had here, and we add the mass term, where did we do it? I can move it here. Then the potential will go down when M is relatively small, touch 0 here, and go up here. And at the minimum here, we find an expectation value for M, which is precisely this value. Indeed, if you look at this formula, and you make all the eigenvalues of the mass matrix M go to 0, you can check that the expectation value of big M round off to infinity. So the picture is that for small mass, there is a large expectation value. As the mass goes to 0, this expectation value moves to the right, until eventually it's kicked out of the system. So for NF less than NC, this is the interpretation of this formula.
Question?
Yes.
For NF less than NC, the effective action we got from the larger M case is also Wilsonian? Is also Wilsonian?
Well, in this case, we see that it's both Wilsonian and 1pi. Everything makes sense. We get the same answer. Her question does not arise because the rank of M is not constrained. The expectation value of M is understood as some property of these quarks along the moduli space of vacua. The determinant, the rank constraint is satisfied. Everything makes perfect sense. So for NF less than NC, this is both 1pi and Wilsonian. It's valid along the flat directions, everything. The interpretation is obvious. It took about 10 years to find the proper interpretation of these formulas when
when the number of flavors is larger. Well, to be honest, not everybody was working on it during this decade. Yes?
I have a question about the Wilsonian action that you have where the masses are very small. We got a Wilsonian action for mesons, and then we can make them massive and integrate them out. Then the Wilsonian action will govern the behavior of less number of mesons. Then if you just integrate everything out, in what sense it is producing?
Well, it's exactly this formula. If you take this formula and let the mass be a matrix which has some zeros. So M1, M2, M3, and then zeros. So that allows you to integrate 3 quarks out, and you have an effective action with a meson M, which is smaller. And so you do that in this formula. You integrate out these heavy guys. It's completely straightforward. It's just algebra. You plug it back in, and you find the formula for the low mass theory with the slightly different values of lambda, because lambda is now corrected by factors of n. And all the factors work, and this would preserve this NC minus NF formula. And if you keep going, you will find the formula we started with for the pure gauge theory. So the formula for the pure gauge theory can be obtained in 2 different limits. When the masses are very big, we first integrate out the quarks, and then we just write NC lambda cube. And if the masses are very small, we start with this, then we integrate out big M, and leave it as an exercise for you to check that you get the same formula. In fact, as I said, it's not surprising, because this formula is unique. So when the quarks are massive, when all of them are massive, this must be the answer. What physics we assign to it depends on whether little m is big or small. If little m is big, you first integrate out the quarks, and then you do the gauge dynamics. If little m is small, first you do the gauge dynamics, find something like this along the modular space, and then integrate out big M. And sure enough, you get the same answer. The words are totally different. Physics is different. And for NF less than NC, when the mass is small, sorry, when the mass is large, the expectation value of big M is small, which corresponds in this picture for the wave being here. And then it makes sense not to think about the flat directions. The mass is big, the potential curves up, and the minimum is not at the origin where naively it is, but it's pushed out a little bit. When the mass is small, the wave of big M is large. So from the first perspective, it's very surprising. We work at the origin, this is a massive theory. How come we get a wave which is so large? We first integrate out the quarks and then the gauge dynamics. This is very surprising. But if you work through this Lagrangian and interpret it a la Wilson, then there's really no surprise, because we're really working on the flat directions.
And the fact that after integrating out all the mesons we get that is clear because that's how we used and transformed it. Back the
That's the proper interpretation when the mass is big. But that's not the proper interpretation when the mass is small.
The mathematical step involved is the same.
Oh, the mathematical step is not only the same, it's trivial. It's trivial and the same. All the formulas are basically the same, yeah. And everything here, up to an overall normalization, is determined by symmetries anyway. So you should not, in hindsight, you should not be so shocked that you find the right answer. So that's the easy interpretation. The only surprising thing here is that the non-renormalization theorem is violated, and the theory is really not near the origin of moduli space, where one would naively think, but it's in fact very, very far. Next, I would like to increase the number of flavors and explain what's going on there, because at that point, we've already seen that these formulas here are very confusing. Your question is then a lot more interesting. What happens to the rank, and so forth. So we'll start with NF equals NC. I'll keep that separate. This is where we keep the important stuff, and this is the work area. So this is what we found classically this morning. That there is a classical modular space of vacua. This is Q tilde, this is that Q tilde, and therefore this equation is true. this is one of these formulas which, in terms of the fundamental quarks, is an obviously true statement. But and therefore, well, that's an obviously true statement, classically. And now we can ask, can we repeat the same story? So we had this modular space of vacua, and then we asked ourselves, can a superpotential be generated along this modular space of vacua such that the vacuum degeneracy will be lifted? Is this possible or not? By now we are a little bit more experienced. We try to write something which is invariant under all the symmetries and holomorphic. And the fact is that there's nothing you can write down. There's nothing you can write down because this is the only thing you can write down. The formula we had there is actually 0. The prefactor is 0. And if you don't like the fact that the prefactor is 0 because maybe we don't control it well, the exponent doesn't make any sense. So in this case, there is no W, no Wilsonian W, which can lift the degeneracy. What does it mean? It means that the classical theory has a modular space of vacua, and the quantum theory should also have a modular space of vacua. See, all these there's problematic interpretations with this formula up there, when the number of flavors is bigger than the number of colors, simply tell us that there cannot be any superpotential. We cannot write a superpotential. The same reasoning also works when the number of flavors is bigger than the number of colors. The rank is 0. How can we put it how can we put it there? This determinant is 0. Or more to the point, this big lambda is in the denominator, so this formula doesn't have the right limit. In the weak coupling limit, we should get 0. The weak coupling limit, lambda goes to 0. And this thing diverges when the number of flavors is bigger than the number of colors. So what the proper statement is that the vacuum degeneracy of the massless theory is not lifted. This is dramatically different than what happens for fewer flavors. But then we ask ourselves, so what does this formula mean? We derive the formula there. It must mean something. One thing is clear. It's not the Wilsonian Lagrangian. Whatever this thing is up there is not the Wilsonian Lagrangian. So this is an example, which I promised you I will have, that you derive the 1pi action when the mass is non-zero. We found this answer. We did it when the mass is large. We can crank the mass down. The mass is not 0, but small. This formula must still be right, but it cannot possibly be the Wilsonian Lagrangian of the massless theory. This was a cause of enormous confusion in the literature. Because you compute this Lagrangian, this is a Lagrangian. What vacuum degeneracy are you talking about? So let's go back to NF equals NC. Something will have to give that formula over there. In fact, if we start with NF equals NC and we give mass to one of the quarks and integrate it out, we should flow down to the previous story, the story with fewer flavors. So start with, say, 4 colors and 4 flavors. No superpotential is present. Turn on the mass term for one of the quarks, crank the mass up. You go back to 4 colors and 3 flavors, and now a superpotential must be present. So how can we generate a superpotential out of nothing? That's the question. We need to write something that once we turn on a mass, the superpotential is generated. And the answer is, I'll just present it as a guess here, but we can actually prove it. Imagine that this constraint, so this is the classical modular space of vacua, claim that the quantum modular space of vacua is the same thing, M, B, and B tilde. It cannot be that different. It cannot be that different because classical physics is not that bad. So the slight modification. So the modification is that we're going to write that M minus which is the same as 3nc minus nf. So what we claim is that the modular space of vacua remains but it is slightly deformed, slightly more mathematically. It was a complex manifold, it was a killer manifold. And this complex manifold has now a deformed complex structure. We deformed the complex structure on that manifold. Originally, let me draw a cartoon of it. The modular space of vacua looked like a cone. Looked like a cone with a singularity at the origin. This deformation of the complex structure is totally negligible when M and B tilde are large, because this is a billion, and this is a billion minus 1, and this is 1. It doesn't change much. But when these are near the origin, this deformation is important. And what it does is to smooth out the modular space. So the quantum modular space, very far, it's similar to the classical one. But as we get closer to the origin, it's deformed, and it becomes smooth. So this is a cartoon of what the modular space looks like. Let's take an example. Imagine B and B tilde vanish. For example, we had a symmetry. Baryon number is preserved, B and B tilde vanish. So if B and B tilde vanish, we say that the determinant of big M is not 0. If the baryon, and if both B and B tilde vanish, the determinant of Q vanishes, and the determinant of Q tilde vanishes, classically. But the determinant of QQ tilde, classically, is 0. Quantum mechanically, I claim, is lambda to the 2nc. Indeed, let's look at the expectation value of the correct formula. If nc equals nf, and we substituted this formula, baryon expectation value is 0. We compute the determinant of this formula, and we get lambda to the 2nc. So just by staring at this formula hard enough, we could have seen how to solve the problem. Because if baryon is 0 and B tilde vanish, then classically that M must vanish. But quantum mechanically, we just compute that M from here, we see that it's non-zero. In fact, it's independent of the mass. So we can compute that M, take the mass to 0, and derive this deformation of the constraint. Another comment about that, we have objects here which classically satisfy a constraint, and classically it doesn't even look like a deep constraint. It's an obvious thing. We take M is Q times Q tilde, symmetrics, and B tilde are again, B is the determinant and B tilde is the determinant. So for every single configuration in the functional integral, we have a 0 on the right-hand side. Yet the full quantum theory does not have a 0 on the right-hand side, but has some constant. So this is an operator relation that classically is one thing. And when I say classically, it's true even without using the equations of motion. It's true for every single configuration in the functional integral. And yet, when we perform the functional integral, that's not true. M, B, and B tilde live on a different space than in the classical theory. But the classical theory is not that wrong. The classical theory is very accurate far out along the flat directions. Now that we have this deformation, we can actually easily put it in the superpotential. So what would the Wilsonian superpotential say? So one way of saying is that we have M, B, and B tilde, and they simply live on this curved space, and there is no superpotential on that space. This is a correct statement. No superpotential on the modular space, and the modular space satisfies this equation. There's an alternate description where I add an auxiliary field X and put it as a Lagrange multiplier and write this superpotential. The equation of motion of X implements the constraint. Another way of saying it is that I'm throwing in two more chiral superfields. One of them is this Lagrange multiplier,
and the other is the direction normal to this constrained surface. We have a surface in subspace in the space of MB and B tilde, defined by this equation. And I'm throwing in another chiral superfield, which is normal to that space. This thing is a mass term for this additional field that I threw in. So therefore, it does not affect the infrared physics. But it makes it very easy to perform computations, because we can now add the mass term and flow down, integrate out the components of M that are massive, and derive the answer for NF less than NC. Which is, again, somebody here said it's the same computation. Who said that? Somebody here said that all these computations are essentially the same. You did? Good. So it's the same computation again. In fact, if we stare at this formula hard enough, one with S, we can substitute NF equals NC here. And if we do that, we get here log of that M times this S outside. So we can identify here S as the Lagrange multiplier, which implements the same constraint when B is 0. But this formula will miss the possibility that B is non-zero. So the good thing about this formula is it gives the correct answer when the masses are there. I could have added the masses here also. So when the masses are not zero, this gives the correct answer, because B vanishes. But the correct physics is there's also B, and we can also add sources to B and get more complicated answers. And then this formula would give us the wrong answer. But if we limit ourselves to the situation where B vanishes, this formula actually gives us the correct deformation of the moduli space. Because classically, the determinant of big M is 0, but quantum mechanically it's not. And if you look here at the equation of motion of S, you can interpret S as this Lagrange multiplier. Again, I emphasize in this case, S is not a massless field, just as the Lagrange multiplier X that I introduced on this blackboard is not a massless field. This is a technical device to implement the constraint. So this is how we get a superpotential out of nothing. We have zero superpotential on a deformed space. And when we integrate out some stuff out of a deformed space, we can get a superpotential. Any question on that? This is clear.
Excuse me, could we have determined the superpotential for baryons in the pure gauge theory?
Sorry?
In the first exercise, which would be for the pure gauge theory.
There are no baryons in the pure gauge theory.
So, I mean, in the sense that, assuming that we have integrated out NF points.
We could have added operators coupled to the baryon operator, in which case we'll get a much more complicated superpotential. I don't think it was worked out in full generality. It worked out in many special cases, but I don't think it was worked out in full generality. Matt could know better than.
I agree. I don't think it was ever done.
But special cases were done. Like NF equals NC was done. Yes?
I'm just curious, so, I mean, you've explained that there's a gap, but is there some way in that you can do something like, look for an area law and a Wilson loop or something, or some...
Excellent question. Does this theory have any area law?
Yeah.
It does?
I'm asking you.
I'm asking you, is there an area law? Before you wanted me to check it, whether there is an area law, whether I can do it. So I can easily do it, and I'm asking you, is there an area law in this system?
I don't know. I asked you.
The answer is there is no area law. When we say confinement in this system, except in the case which is the pure gauge,
Yeah.
but if we are in the theory with quarks, there is no area law. The theory with quarks has quarks.
Well, okay, right.
And if you put external sources, is there going to be a string between them, the same string that people love in ADS and so forth? No, there isn't, because quark will pop out of the vacuum and will screen them.
Yeah.
And when Matt is talking about showers and hadronization and so forth, this is exactly what he does. A quark comes out, and creates a long string behind it, but this string breaks by creating more quarks out of the vacuum, which break the string and attach to the original quark and make mesons, baryons, whatever. So this theory doesn't have an area law.
But in the pure gauge?
In the pure gauge, there is an area law. Adding quarks is not going to help, because by adding quarks, we ruin the area law. So what can we do? Well, we can add quarks in the adjoint and look for an area law there, because then there is an area law. And indeed, when you add quarks in the adjoint and you repeat the same, it's not just one lecture, or need maybe 2 more lectures, but if you do the same thing with quarks in the adjoint, you derive the area law. In fact, you see the physics behind the area law, which the area law arises from monopole condensation. And there you can see it very vividly.
You mean by making it n equals 2 or even n equals 1?
Even n equals 1, don't need to be n equals 2. But n equals 2 is a special case. In fact, in n equals 2, there is never an area law. So what you really need is to take n equals 2 and break it to n equals 1.
Yeah.
But you can also take n equals 1, which has nothing to do with n equals 2, and still derive an area law in a similar fashion. You can play the same game not in SUN theories, but in SON theories, and put the quarks in the vector representation, in which case you would expect an area law, because quarks in the vector representations cannot screen a Wilson loop in the spinor representation. So you can ask this question. Let's do SON. So your question could have been, repeat the same story, not with SUN, but SON. Because you would have said, well, this theory should have an area law. Can you see? The answer, yes, you can. And you can see that it comes from monopole condensation. Okay, so that was the easy part, NF equals NC. But if we try to make the number of flavors larger, this trick doesn't work. So we cannot simply deform the modular space of Acula. We need to do something a little bit more dramatic. And if you start thinking about it, you immediately see that all the simple things don't work. Because again, the modular space of Acula cannot be lifted. If the theory is massless, we had a modular space of Acula. Even for NF equals NC, it's not lifted. For larger values of NF, the same thing is true. It cannot be lifted. As I said, lambda there is in the denominator. We cannot have lambda in the denominator. It doesn't satisfy the rules. So what is the correct physics? We need to find something that will make sense when m equals 0. We'll have the correct moduli space of Acula, is this theory. And yet it is such that when we deform it by turning on masses, we flow to these formulas, because these formulas cannot be totally wrong. They're very wrong as Wilsonian action. We've already seen that. But they cannot be completely wrong, because after all, they give us the correct expectation values. So I could motivate the answer, but instead, I would just give the answer as a guess and show some of the consistent definitions. Before I do that, are there any questions on this? No. So the idea is to use something called duality. What is duality? Duality is two theories which have the same physics. I've already formulated the question in such a way that it asks to be answered by duality. It really begs to do that. We have a theory, the theory we started with, and it has some modular space of Acula, etc., etc. And we know what happens when we turn on masses. It does this. Can we find anything else which looks simpler, which at long distance, which is the correct description at long distance, such that when we turn on these masses, so it will have exactly the same modular space of Acula, and when we turn on the mass over there, we reproduce this expectation value. We managed to do that when the modular space was deformed. This was a kind of a primitive way of giving a dual description of the theory. Now the dual description is a little bit more sophisticated.
So the language I will use, again, same as electromagnetic duality in Maxwell's theory. I refer to the original theory as being the electric one. These are the quarks and the antiquarks. And I'll postulate the existence of what I'll call a magnetic theory, which I claim is the same at long distance. So far I have not even said anything. Just said that this is the question. Find another theory which is the same at long distance. And now we just have to guess what to put in here. So I'll give you the guess. The guess is that there is a gauge group I'll call these magnetic quarks. We call these magnetic antiquarks with tilde, because they are also chiral superfields. And in addition, we introduce our field M, and I will let this M have arbitrary rank, unlike the M on the modular space of vacuum. So this is a fundamental field, not a bilinear. It's elementary. Fundamental field, not a bilinear. Which in the end will play the role of the bilinear in the other theory. And if you look at the quantum numbers, we can put a superpotential at tree level in this theory, which would be Q and Q tilde. And now let me put all the transposes in the right place in the trace. And in view of time, I'll be brief.
And it's SU for both.
Yep, thank you. So this is the magnetic theory. A gas pulled out of my hat. And this is the electric theory. These are two separate theories. They have different gauge groups. The two gauge groups have nothing to do with each other. It's not that one of them is a subgroup of the other. These magnetic quarks have nothing to do with the electric quarks. In fact, they turn out to have fractional baryon number. The objects in this theory cannot be described in a local way in terms of the object in this theory. The objects in this theory are described in a non-local way in terms of these. And the claim is that these two theories are actually the same at long distance. So these are two separate theories, and they are as separate as different. They have different number of fields, different gauge group, and yet they are the same. So this might sound a little bit unbelievable, so we have to check it. And what can we check? First, we have to check that these two theories have the same symmetries. I cannot do that. The two theories have the same modular space of vacua. I don't have time to do that. If we turn on masses in this theory, we can turn on masses here by turn on a term linear in big M. And again, we're saying the same answer. So we know how the electric theory flows to a theory with fewer flavors. This theory will also flow to another theory. The gauge group will change, but we get the same answer. Get a commutative diagram in the flows and stuff. And we can check that all the gauge invariant operators are the same. We can form baryons out of the magnetic quarks. We can form baryons out of the electric quarks. So let me just do that for fun. The baryon, in terms of the electric quarks, is roughly Q to the NC. There is an epsilon tensor and so forth. In terms of the magnetic quarks, this is Q to the
minus NC. Because the number of colors is different here, so we have to raise this little cube to a different power. And you can check that these two objects have exactly the same quantum numbers. So these two theories look different, but they are in fact the same. So instead of presenting all the consistency conditions and how they work, I'll tell you what happens when we change the number of flavors and the interpretation of this story changes. And we'll start from below. We had this NF equals NC theory. So now let's discuss one step at a time. So for NF equals N, so we had this. And for NF equals NC, we had this modular space of vacuum, which was deformed. So now, right here, NF equals NC plus 1. This is particularly easy in the magnetic description. The magnetic description has no gauge fields, so that's easy.
Question?
Yes?
What if NF is 2NC?
NF is 2 and C. There's nothing special at this point.
But it seems in the magnetic theory we've got extra N.
Sorry?
Like, in NF equal to NC, the gauge group, like the same and the flavor.
It's the same, but it's not the same gauge group. It's isomorphic as a group. But the magnetic gluons and the electric gluons have nothing to do with each other. The gluon here is not, you cannot write A mu of this equals A mu of that. This formula is wrong. It just so happens that they both have the same indices. There's an example of this in Maxwell theory in 4 dimensions. Turn off all the currents and all that in Maxwell's theory. So Maxwell theory, you can introduce an A mu. Do you know how you do that? So you introduce an A mu in Maxwell theory. But in fact, you can introduce A mu in more than one way. You either say that the B, either you say that F mu nu is D mu A mu, or you say that the star of F mu nu is D mu A mu. In other words, B is grad A, or E is grad A. Which one is right? Both are right. It's more conventional to say that B is grad A. The reason is that in nature we have electric charges and we don't see magnetic charges. But in a hypothetical world without electric or without magnetic charges, physicists in that world, if there are any, maybe somewhere else in the I won't even finish the sentence. So there could be a U1, and the U1 might not have any electrical magnetic charges. And then they could have a debate. Should we introduce A mu such that AI is grad? So that B is curl A, or should we say that E is curl A? And will E be grad phi, or will B grad B? Will big B be grad phi? And there are 2 ways of doing it. In fact, there's more than 2 ways of doing it. Which one is right? All of them are right. What's the gauge group? It's always U1, but it's not the same U1. If one photon has a U1 and the other photon has another U1. Are these U1s the same? No, they have nothing to do with each other. Can you write one photon in terms of the other? Yes, in a non-local way. In fact, it's not uniquely determined because it's up to gauge transformation. So you have to invert some differential operator to write the electric photon in terms of the magnetic photon. Is there anything wrong with this? No, it's perfectly right. This is called duality. So for NF equals 2 and C, it just so happens that the 2 groups turn out to be the same group. But physically, they are different gluons.
You generally have the numbers of gluons.
Yep.
How would you, what's the meaning of that?
I don't see the problem. They're not the same, so why should they be? If they'd been the same, then I would have had to explain it. But they're not the same. I'm not claiming that the gluons of one are the same as the gluons of the other. These are 2 different gauge groups. In fact, this leads me to a very, very general point that I've been advocating for some 15 years now, maybe more.
Gauge symmetry is not fundamental. I think this makes it completely obvious. And all your questions stem from the fact that you expect the gauge symmetry to be fundamental. I said already this morning that gauge symmetry should not even be called a symmetry because it doesn't act on anything. The Hilbert space is gauge invariant. So we see it here. We started short distance with one gauge group. We end at long distance with another gauge group. And the gauge group that we end up with at long distance has nothing to do with the original one. So we started short distance with quarks and gluons, very much like the quarks and gluons of QCD, ordinary QCD. And at long distance in QCD, we find pions and Rho mesons and so forth. There's a long list of particles. And in this theory, we also find a long list of particles, these magnetic gluons. Are you surprised that there are pions in QCD? You started with quarks, you end up with pions. Here you start with quarks and you end up with these guys. The only thing which is surprising is that the guys you end up with carry some exact, unbroken gauge symmetry. And we were brainwashed, you were less brainwashed than I was, that gauge symmetry is fundamental. You can't get gauge symmetry out of nothing. But here is an example. You get gauge theory out of nothing. But in fact, if you go back to Maxwell's theory and the example of the two photons, if we start with the electric photon, we write Maxwell's equation, then we realize that there are only E and B are meaningful. So we write Maxwell's equations in terms of E and B. And a smart graduate student say, oh, these equations are interesting. We can introduce another A nu. And this another A nu has its own gauge invariance. Is this new gauge invariance that this graduate student discovered, is this new gauge invariance fundamental? And the professor would say, of course not, because we started with the electric photon with its gauge invariance. That was fundamental. The magnetic one that you found was some stupid derived concept. And that professor would be wrong, because both of them are equally fundamental. Or more precisely, neither of them is fundamental. If you want a slogan for that, gauge symmetry is not a symmetry. Gauge symmetry is a redundancy in our description. We need gauge symmetry because our theory is non-local. The only way to write the theory in a manifestly local way is to add redundant degrees of freedom which have no physics in them. These are these gauge modes. So you can always take any theory and declare that it's a gauge theory for anything. Take any Lagrangian you want, in any gauge group you want, and I'll write for you a gauge theory which has your Lagrangian as the correct description. For any group and for every Lagrangian. Doesn't matter. It doesn't even have to be a global symmetry. That's the problem. The reason is that what we do is we add non-physical degrees of freedom. And the reason we add them in gauge theories is in order to make locality manifest. That's the main thing. We would like a local description. And for local description, we need to add some extra baggage. These gauge degrees of freedom which are not really physical. And what's the idea of duality? Duality is the same theory with its which looks almost non-local, and it can be made manifestly local by adding two separate, distinct set of unphysical degrees of freedom. Either the electric degrees of freedom and its gauge symmetry, or the magnetic degrees of freedom and their gauge symmetry. And we can make a choice. We want this description or that description. But this is not more than some extra stuff that we threw in the system in order to have a local description.
Just because they have more operators in one field.
No, they aren't. They aren't. They are more non-gauge, non-invariant operators. But gauge non-invariant operators is not something we should ever discuss. The thing to write down is the complete list of all the gauge invariant operators. And surprisingly, this theory and that one, and in the remaining 10 minutes I cannot explain that. Surprisingly, this theory and that one have exactly the same gauge invariant operators. Here is an example. And it's actually quite, if you work it out in detail, it's quite miraculous that this thing is true. Because this has barrier number. You can see that the barrier number, if you want B to have barrier number 1, big Q should have barrier number 1 over NC. And little q should have barrier number 1 over this. There's also an R symmetry in the problem. So this should have a certain R symmetry, and this should have another R symmetry. And once you have different symmetries, you have to make sure that the mesons you make out of them have the correct R symmetries.
it's not obvious that what we call M here, which is a fundamental field, is exactly the same R symmetry as the quark bilinear. So here is another element in this dictionary between the two theories. The meson of the electric theory, we had this operator. In the magnetic theory, this is the fundamental quark, the fundamental field M. So they look different, but they are in fact the same. So the story is a little bit richer. I will not even describe this one. So in the remaining 7, I have 8 minutes and 3 more that you owe me from the morning. It was actually 2 more.
Injury time?
Sorry?
Injury time?
Injury time, correct. Are you talking about the Celtics, or are you talking about the soccer games?
Soccer.
Because I think in basketball there's no injury time.
No, he's not.
This doesn't count, it's timeout. So I'll say a few words about what happens as the number of flavor changes. So this is the boundary of asymptotic freedom. Matt had similar boundary, but this number 3 was slightly different. So if the number of flavors is bigger here, no asymptotic freedom. So the electric theory is free in the infrared, just like massless QED. As we go to higher and higher energy, the gauge group becomes stronger and stronger, the interactions become stronger and stronger, and eventually we hit the Landau pole. At low energies, on the other hand, this theory is very weakly coupled, and at extremely low energy, we have free quarks and gluons. As we make the number of flavors smaller, all the way up to NF equals 3.5 NC. In this case, the theory, electric theory, flows to a non-trivial fixed point. In other words, this is a superconformal field theory. And this was mentioned by such a phenomenon was mentioned by some of the speakers here. So in this window, it's called the conformal window, the electric theory is interacting. It starts flowing. The gauge coupling becomes slightly larger and larger and larger, and then it stops. It stops at some finite value where the theory is interacting. We can do the same computation in the magnetic theory. The magnetic theory is a different theory. It has different degrees of freedom, different gauge group, and so forth. And this theory flows in the infrared to exactly the same fixed point. So somebody asked me in my first lecture, what about the number of degrees of freedom? Well, I emphasize that in field theory, the number of degrees of freedom is not concerned. It's not well defined. Here we see 2 different theories with different number of degrees of freedom, and they flow to the same fixed point. What happens in this regime? In this regime, the gauge coupling of the electric theory comes stronger and stronger and stronger, and goes all the way to infinity. The electric theory is genuinely strongly coupled. But we have a little surprise with the magnetic theory. Because the magnetic theory has NF flavors and NF minus C colors. And if you ask yourself, when does this theory cease to be asymptotically free? It's exactly in this window. And this is an exercise you can do as I talk.
and see that this is the boundary. So here the magnetic theory is IR free. So what happens to this picture? Here is the electric theory. It flows in the infrared, and it reaches somewhere. What it reaches is the magnetic theory. The magnetic theory is infrared free. So it has a certain irrelevant direction along which we come from the electric theory. And the magnetic theory describes the infrared. This is the most dramatic regime because we start with free gauge fields and free quarks at short distance. We end up with free gauge fields and free quarks at long distance, but they are not the same. So in QCD, we start with free quarks and gluons at short distance, and we end up with free pions at long distance, slightly interacting. These guys are also slightly interacting. In that sense, we solved the theory. We formulated the question, what happens at short distance? And we gave the answer, if what happens at long distance. As I said, this is what physics is all about. Formulate the question at short distance and find the answer at long distance. In the remaining 4 minutes, I can either answer questions or I can outline how all these formulas can be re-derived. That would take a little bit more than 4 minutes. Or I can put...
Lorentz boost.
Sorry?
You can have a Lorentz boost.
Lorentz boost? That won't help. Maybe it will hit my red eye when I go back home. So when you asked me what I was planning to do in the remaining lectures was do justice to this story, which I didn't have time to do, and use all this understanding of the dynamics to show how we can, so here supersymmetry is unbroken, but we can use this understanding of the dynamics to show how to find new mechanisms for supersymmetry breaking and find nice models in which the scale of supersymmetry breaking is dynamically generated, and we can use this as a building block or a module in a general theory where we have supersymmetry breaking, some mediation mechanism, and the MSSM. So that was supposed to be the remaining, at this rate, the remaining 7 lectures. So I think I'll stop here unless there are any questions. So this presentation, what was the quickest, was probably the clearest, because there are no questions.
The theory that is IR free, the magnetic theory, which we have by delivery. I mean, we are saying that theory only makes sense in IR, right? It's not like the theory is making sense.
Yep, the same as pions. Is the theory of pions a good theory? Yes, it's an excellent theory. It makes lots of useful predictions. Is it a complete theory? No, because we have to add to it high dimension operators. The complete theory is the theory in the UV. The same thing is true here. But we basically know what the right degrees of freedom are. And she asked me about the rank of the matrix M. This M at long distance, M is a free field. This meson is a free field, and it has the full rank, NF squared degrees of freedom. Even though microscopically it looks like it has less.
So are we saying that if we find a theory that is not asymptotically free, then we shouldn't discard it, but there could exist some other description of the theory in some other degrees of freedom which is asymptotically free?
Yep. QED is an example. Pions is an example. So pions, we know the replacement. For QED, we don't. But this doesn't make QED a bad theory. QED is a better theory, and the phrase people use, it needs to be UB completed. We need to add degrees of freedom, or throw the degrees of freedom we see and get something else instead. The new thing here is that for QED, what people try to do is to add degrees of freedom to make the theory sensible at short distance. Then maybe it's embedded in string theory, or maybe it's embedded in another field theory, which makes sense. For example, SU5. What we say here is No, you don't just throw in additional degrees of freedom. You throw out what you have and throw in something totally different. And magically, the strong coupling of these what is now viewed as fundamental degrees of freedom generates the others. So whether one can make the standard model out of this is time will tell. People try. Sometimes it works better, sometimes it works less, but there isn't yet a gold-plated model.
So do we know what happens for n equals to 2 theories when the flavor is greater than 2 in C?
Well, we know in the sense that you can give the low energy description. We can deform it by giving masses to the flavors.
But the UV completion of it?
Well, why do you ask about n equals 2? You can ask the same thing about n equals 1 with more flavors than colors here. Or in fact, you could ask the same question about ordinary QED. No supersymmetry at all, just electrons and photons. This theory works extremely well. Some 8 significant digits or maybe more. It's not asymptotically free. There's nothing wrong with it. And one day we'll know what to embed it in. But this doesn't make the theory useless. I emphasized in the first lecture that quantum field theory do not have to be renormalizable. This is an example of not, here the lack of renormalizability kicks in non-perturbatively, not in perturbation theory. Perturbation theory is renormalizable, but non-perturbatively. But we can add things which are even perturbatively non-renormalizable. What does it mean? Well, all it means is that a certain energy, higher than the one we discussed, the description should change. This does not make the description bad. So if you want to take lessons from these lectures, I would say the first lesson is field theories don't have to be renormalizable. And the second lesson is gauge symmetries are not fundamental. And the third lesson, in fact, I would say no symmetries at all. And the third lesson is what you view as fundamental and what you view as composite is a question of description. Even that is not universally accepted. For example, here, the meson is fundamental, and here the meson is composite. So how do you decide what's fundamental and what's not? Depending on what's useful. Sometimes it's useful to have one description, sometimes it's useful to have another. I think I'm more than, yeah.
So, can I just clarity, all of this was in 3+ amperes? Is it dimension dependent, this picture, or is it?
The details, yes. The philosophy, no. So the details of what I did here, I did an example. The word did was used very liberally here. I just stated the answer and I didn't even have time to explain all the features of it. But this thing was done in a lot more detail. And all the details are very specific to 3+1 dimensions. For example, asymptotic freedom when NF is bigger than 3 NC. It's also specific to the particular gauge rule, SUN. You can repeat the same exercise with SPN, or G2, or SON, or SPN, or products of groups. A product of group is bifundamental. You can do whatever you want. 3-index antisymmetric, and you get different answers. This technology helps there. You ask, what about 2+1? So some papers were written about 2+1, less than in 3+1. The technology is basically the same. The phenomena are different. So there's an unorthodox description of supersymmetric theories. It's another TASI lecture. Person behind you. And he actually emphasized the relations between 4 and 3. And you can do the same thing in 2 dimensions. You can also do the same thing in 5 and 6 dimensions. You're not limited to this. And the phenomena are really different. But again, I emphasize that the technology is the same. What is really needed is not so much to apply this circuit. It was nice to apply this technology to other examples. What I think what is really needed is to find a new technology. So the ADS-CFT is a new technology. It allows us to analyze many more theories. So there's a theory you would like to solve. It has a gravitational dual, and then we do some calculation on the gravity side, translate the answer to the field theory, and we get some new insight to the field theory. But what young people like you should do is really find yet another technology which will uncover new insights. And then you can come to TASI and lecture about it.